sort of giving a review of a few things that we have been working on over the last couple of years, and it's particularly great that several collaborators involved in this project are here. So Fabian and Richard, who are no longer at Harvard, but started many of the important work in Tushar and Mario's continuing, and many ideas go back to the work started by Dimo when he was still at Harvard. And what makes this work particularly exciting is that it's very cross-disciplinary, so you'll see that, let's say, even though most of my talk, well, actually it will be a combination of sort of cold atoms and traditional solid-state physics, and in the context of cold atoms, it's really a collaboration with Emmanuel and his group, and with Marcus and his group, that really sort of allowed to make progress and provided a lot of motivation for what we're doing in the context of condensed matter. It's we have been discussing quite extensively with a group of Andrea Cavalieri, and it was also very kind to allow us to show some of the unpublished data. Okay, so let me start with a somewhat extended introduction, and I want to emphasize one general point that when we think about traditional solid-state systems, and let's say I have been teaching introductory solid-state physics in the post-semester, I'm teaching many-body physics, but really the central idea of traditional many-body textbooks is response functions and two-point correlation functions. Right? So many of the and so basically we sort of what we usually learn in solid state is many-body systems in equilibrium and some kind of linear response paradigm as the only form of dynamics relevant for understanding experiments. And this is something that you have been learning in the last couple of days. Is no longer true in some of the novel systems, but let's say just to connect to what traditionally is being taught, if we take seemingly very diverse systems, for example, we can take STM experiments, right? So you bring a tip, you inject electrons into a solid, and then we measure the local density of state, which is basically kind of differential conductance as a function of voltage and position, and it's really determined by really operators of creating and annihilating electrons, and the frequency is just set by the voltage to the tip. Or if we look at scattering experiments, usually this is something like scattering of photons or scattering of neutrons. Then the general framework is that we have a particle coming in. For example, in this case, it can be a photon, and and then it's scattered, and we're looking at momentum transfer and energy transfer, and this intensity of scattering is just given by the density correlation function. And now, sort of both of these kind of frameworks, like looking at systems in equilibrium and also probing linear response functions, are being challenged by the new generations of experiments. So you already heard about systems which are very well isolated from the environment, and so they can actually support coherent many-body evolution for long times. But also some of the techniques rely heavily on non-equilibrium dynamics. So, for example, a lot of scattering experiments is being done with resonant X-ray scattering. And the way it works is that you, when you send in a photon, you tune its energy in such a way that it resonantly excites electron into the conduction band, and the dynamics that it gives rise to actually has to do with this core pole exciting many electrons or collective modes in the many-body state. So in order to understand cross-section, one really needs to explore the full non-equilibrium dynamics of the many-body systems. Then another quite active field is bump and probe experiment, and I'll talk about one example of this, which is photoinduced superconductivity. by creating a non-equilibrium state, we can try to reach states which are not available in equilibrium. And then you heard about NV centers and ultra-cold atoms as really these kind of new examples of systems where they're so well isolated from the environment that you can drive them out of equilibrium, make some kind of quench experiments, or sort of like some kind of Floquet driving, and we'll hear more about it later in this school. But of course, theoretically, it is extremely challenging, and we'll talk about some of the approaches for describing this out of equilibrium dynamics. So let me also give you another motivation which comes more from the condensed matter side for looking at systems out of equilibrium. So a lot of history, right, of science is driven by trying to find new materials with new properties. Of course, it started, the obvious route is to just do different chemical compositions, and we can, even research continues even these days with, say, materials like graphene or new high temperature superconductors. But then people realized that it's not enough to just take sort of naturally occurring type systems, and then the idea of metamaterials came up that one can modulate properties of matter periodically in space, and therefore reach new types of functionality, such as, say, negative permittivity materials, which connects all of these kind of connects to all these kind of cloaking applications. But when we talk about time dynamics, you can think about it as just a new type of control, right? That we no longer control just spatial structure, but rather we control materials in time. Right? We can periodically modulate, say, parameters of the Hamiltonian, and there was some very striking demonstration recently, such as observation of photoinduced quantum Hall effect, or there have been quite a few photoinduced phase transitions. So states which, let's say in the simplest case, it would be states which would be metastable and would not exist as, sorry, in this case, let's say in equilibrium. So this state would be metastable, would not exist in equilibrium, but after we drive the system can become a local minimum, so we have photoinduced state. Again, just to point out the challenge of understanding dynamics in contrast to equilibrium, to dynamics near equilibrium, to what we can study using linear response, is just the type of problems that we have to solve. So when we talk about small fluctuation around the ground state, we have to look at a very tiny portion of the entire Hilbert space, which scales as just polynomial of the system size. But when we look at very far out of equilibrium dynamics, generically we can excite any state in this Hilbert space, so we have to deal with exponential number of states. So one of the central themes of my talk will that for many, actually it turns out that life is not so bad, but for many practical purposes, we can describe non-equilibrium dynamics without taking into account all the possible degrees of freedom, and still looking at sort of largest subspaces that you need for describing equilibrium, but still ones that scale polynomially in the number of degrees of freedom, in the number of particles, and that this still gives us sort of a decent description of many experiments. Okay, so with this I can sort of move to the actual talk. So this is briefly the outline of my lectures. I'll try to give you one example of very non-trivial states of matter, or very non-trivial control of matter, and this will be using coherent drive, and this will be in traditional solid-state systems. So this will be photoinduced superconductivity, something that we call Higgs amplifier. We'll see where this name comes from, and so this will be probably what we'll focus on during today's lecture. This is really just a motivation that when we look at dynamics, then we're connecting to some real-world experiments and potentially to some applications. And then I'll give you the subsequent two lectures will be more technical. I'll introduce a variational approach to many-body dynamics, and I'll show you for systems such as bosonic systems and harmonic systems. And but again, I'll try to sort of connect them to some real experiments. So we'll talk about some non-equilibrium dynamics of quantum type models or terahertz experiment, terahertz STM that have been done recently in Hamburg. And so here you will see that we'll actually have to deal with non-equilibrium dynamics of one of the paradigmatic models in condensed matter physics under symmetry. Okay, so let me start with the story of Higgs amplifier. Let me first remind you about what is a Higgs excitation, and I'll just give us a very generic picture. If we have a state of broken symmetry, right? So then we're used to representing this as something like effective Mexican potential, Mexican hat type potential, right? So we have a minimum, and then we say, well, the symmetry is broken, so we can think of some kind of particle at the bottom of this potential, representing this one of the broken symmetry states, and then we can have fluctuations which are at the bottom of this potential, and this is the usual Goldstone modes. Or we can have fluctuations where this kind of state, basically we can think about this as a particle climbing up and down these walls, right? And that actually corresponds to the change of the amplitude of the order parameter. And that's what we call Anderson. And obviously you have seen this plot from LHC observation of the Higgs excitation in proton-proton collision. And I don't know, Emmanuel, if you showed this kind of comparison, so that's something that is one of my favorites. So in order to observe this Higgs excitation, the collider, they had to do experiments at energies which are 12 orders of magnitude higher than the room temperature. But actually within 1 week of this experiment, of this the famous press conference at CERN, a paper came out by Emmanuel and collaborators where they also observed a Higgs excitation in ultra-cold atoms. And in this case, to see the Higgs excitation, they had to do measurements at energies which are 12 orders of magnitude smaller than the room temperature. So we're talking about energies which differ by 24 orders of magnitude, but we have this universal underlying physics which manifests in a very similar way. So I don't know if Emmanuel will cover this idea of this kind of Higgs, but roughly what you have to do is you need to deposit energy into the system, like in the case of energy collision. This was just the kinetic energy of protons. In this case, they modulated the lattice, and this modulation of the lattice was at a given frequency, which was the same as changing the energy of protons. And you see that there is a resonant, just here you can see a resonant process. The energy matches the Higgs, there is a peak. So here when the energy matches, modulation frequency matches the Higgs, there is a peak in absorption. And actually in the case of cold atoms, once you increase the excitation, go all the way to zero at the transition between the superfluid at the mod phase. Okay, so now let's talk about energy scale somewhere in between, right? We saw cold atoms, which was sort of like nanokelvin temperatures. We saw ultra high, very high energies in accelerated physics, but then it's sort of like in a more reasonable few Kelvin temperature. Higgs excitation can also be seen in a superconductor. Again, it's an oscillation of the superconducting gap. And it's also done in a pump and probe experiments. So details not so important, but you can say that, okay, the first pulse comes in, and then they use the second pulse to actually probe the magnitude of the gap as a function of delay with respect to the first pulse. And what they see. Like basically what this curve show is this gap, right, as a function of time, and we see oscillations which happen at the frequency which corresponds to twice the superconducting gap, which is the frequency at which we expect to see the Higgs oscillation. Okay, and so what we'll see later on that this Higgs excitation actually can have quite dramatic consequences on electromagnetic properties of the medium, and how this has been seen in recent experiments. But before we go there, let me say a few words about photoinduced superconductivity. So this this actually is a sort of a field which explored several materials. I'll focus on just one specific class of materials. So this is a bucketball superconductors, K3C60, and so we have this an FCC lattice. And one of the simplest way of probing superconductivity is through optical measurements. So basically you send light, you measure reflection coefficient from which you can extract real and imaginary part of the conductivity. And this is the system in equilibrium. What we see in the normal state, the real part of conductivity is finite at small frequency, right? That's just our Ohm's law. When that's happening, the system becomes superconducting, this blue line. There's a quasi-particle gap that opens up, so the quasi-particle continuum starts around 10 MeV. At the same time, if we look at the imaginary part of the conductivity in the superconducting state, we see one over omega tail, which develops at small frequency. The way to understand this tail is to just think about, this is what's known as London equation, right? So what replaces Ohm's law for superconductors in usual normal metals, right? Current is proportional to electric field, but when you do not have resistance, electric field accelerates the current, right? So the time derivative of the current is proportional to electric field, and from this we immediately find that the conductivity is I over omega, right? And that's exactly this superfluid. So in real part of conductivity then is 0, and the imaginary part goes as 1 over omega, right? So that's the hallmark of superconductivity. And then what was found in experiments is that when they send light, which is actually it's not resonant with this kind of with energy of quasi-particles, but rather it's resonant with phonons, we'll see it in a second, then they can see very similar signatures as an equilibrium, but now at higher temperatures, right? So here it's already temperature slightly above Tc, but well, noticeably above Tc. Again, we see a gap opening up in real part of conductivity, right? And we see 1 over omega tail in the imaginary part of conductivity. And now you can see this temperature, which is already 5 times higher than Tc. Again, there is a gap opening up in the real part of conductivity, and 1 over omega tail in imaginary part of the conductivity. Okay, and then there is also unpublished result that's a kind of more recent finding that actually, if they change the protocol, how they excite the system, then they can get even more confusing behavior of the materials, right? Because if you think about it, okay, so if real part of conductivity is 0, right, so energy is not absorbed, this means that light is perfectly reflected, right? So reflection coefficient should be 1. But what they found experimentally is when they used shorter but more intense pulses, so just technologically it turns out that the total energy in the pulse has to be conserved, but when they put more energy into a shorter pulse, then they can get reflection coefficient of the probe pulse. You know, so there was a pump which excited the system, then they want to probe this photoinduced superconductivity, but they get reflection coefficient which is bigger than 1. Right? Of course, there is no conservation, violation of conservation of energy, because we're looking at the non-equilibrium state, and therefore the fact that we're getting more light out than the incoming beam just shows that we're extracting some energy which was stored by the pump. But it's still very surprising for how can we get this reflection coefficient greater than 1. And as I'll hopefully to attend with this talk, you will see connection between this experimental fact and the Higgs excitation. Okay, but let me first start by explaining to you how surprising it is to have non-equilibrium superconductivity coming from phonons. So let's go back to how we explain conventional superconductivity in the first place. This is usually explained using the so-called mattress effect. So we know that the first electron comes in, distorts a lattice, right? So we get kind of a positive spinning cloud, and this attracts the second electron. So that's how we get attraction between electrons mediated by phonons. More formally, we can think about it as second order perturbation theory. So the first electron emits a phonon, right, and then this phonon is absorbed by the second electron. So let's try to compute this the characteristic strength of this process. So okay, second order electron-phonon interaction, so we have G squared. Then we have to put energy denominator. Our initial state had just electron at momentum k, right, and our intermediate state has an electron now with momentum p and an extra phonon. And then the first idea is, well, okay, but now if I look at a situation in which I have some phonons, right, we said, oh, I'm actually looking at a system in which I have strongly pumped the phonons, then I should get Bose enhancement factor 1 plus n. So then, okay, we're also interested in BCS type superconductivity. Electrons should be near the Fermi surface, so let me just assume that the energy of these electrons are the same. So we get this usual electron-phonon coupling square divided by the phonon frequency, but there is a Bose enhancement factor, which seems to favor superconductivity. Well, but then, so this is good news of having phonons in the system, but then there is also bad news, because if we already have phonons present, then we have to include not only contributions when we create one extra phonon, but also contributions when we actually, the first electron absorbs one phonon, which is then re-emitted by the second electron. And this process now goes through an intermediate state, which has one fewer phonon, right? Therefore, it comes with the opposite sign. And so now you can see that this contribution actually, and it also has, now it has just the number of bosons as a factor, and this corresponds to effective repulsion. So if we add the two contributions, we find that effective interaction actually no longer includes like this, the number of phonons drops out, and that's where the usual kind of expectation comes in, that only virtual phonons can cause superconductivity, but real phonons do not make any difference. And that's why it was so surprising that by making non-equilibrium state of phonons, we can actually cause superconductivity. Okay, so let me just give you kind of qualitative ideas of how we can get around this seemingly fundamental objection. So let me remind you that when we think about phonons, we're basically thinking about harmonic oscillators. And now, again, let me first kind of throw this at you, and I'll explain where this comes from later. Let me assume that these oscillators are not our usual equilibrium oscillators, but they're excited in a very particular ways. They are experiencing what's known as parametric drive. Basically, you can think about this as like a spring constant, right? A harmonic oscillator being periodically modulated in time. Right? So, okay. Now, so we know how to compute effective electron-electron interaction mediated by static phonons. Now we're asking, oh, what about phonons which are being parametrically driven? What is the effective interaction that they will induce? So actually, I want to argue that effective interaction can be related to correlation function of the phonon displacement. So again, this Q, in this case, if you think about it, it really corresponds to just like position of harmonic oscillator relative to their equilibrium. Right? So what we have to compute is just correlation function of phonons. But now this correlation function has to be evaluated not in equilibrium, but in this driven state, in this parametrically driven state. So let me just give you a qualitative argument how it works. We have our, let's represent our Hamiltonian, so H is our harmonic oscillator Hamiltonian, and now we couple displacement of the oscillator to some external field phi. And we know that when we have external field phi, we'll induce some displacement of the of the position of the oscillator, right? And the coefficient is just given by this response function, right? By its susceptibility, and the same susceptibility actually gives us the change in the energy of the system, right? Because we know that if we apply external field, we will lower the energy by amount which is quadratic in the applied field with a free factor given by this proportionality coefficient. And now if you think about interaction between, and the same coefficient, right, as we said, can also be computed as a correlation, right? It's just response function, but it's also given by the fluctuation. If you think about interaction between electrons and phonon, right, so this is the displacement of the phonon, it's coupled to the density operator for electrons. So from the point of view of the phonons, the density of electrons is like an external field. So if I integrate out if I integrate out phonons, right, I should get an effective lowering of the energy, which is proportional to the square of my external field, which means which is proportional to the square of the electron density, right? And the coefficient is again this response function. So again, it's kind of hand waving, but one can actually make this argument more precise. So therefore, if we want to compute an effective interaction between electrons in a non-equilibrium state, we just have to calculate correlation function of the phonons, but in a non-equilibrium state. Okay, well, fortunately, this is a problem that's relatively easy to solve, because even though this is a time-dependent Hamiltonian, notice that it is still quadratic, right? So if we write equations of motion, they're still linear, right? So they're only, they look like familiar harmonic oscillator equation, except that now we have this external drive, which comes from modulation of the spring constant. And so what we know for this linear equation is that we can always relate the displacement at later time to displacements at earlier time, or let's say momentum at earlier times through some kernel, right? And these kernels are determined just by equations of motion, right? These are linear, and remind that in linear equations, basically relation between initial position and momentum and the final position, they do not depend on this initial state, right? This is something which is determined entirely by the Hamiltonian, by the time-dependent Hamiltonian. And what this tells us is that if we look at our correlation function, right, of the phonon position at different times, so we can relate position of the phonon at a later time, say to the phonon position to momentum at an earlier time, so this becomes just canonical commutation relations. So therefore, the correlation function that we are looking for is nothing but this kernel of propagation, right, from the momentum at earlier time to the coordinate at later time. And as we said, well, what we see here is, what we said already, is that this kernel does not depend on the initial state. So it depends on the Hamiltonian itself, the fact that we have non-equilibrium Hamiltonian, but the number of phonons does not matter. Therefore, we're actually perfectly consistent with the objection that we gave before. However, we see that this kernel can now be different because our phonons are trivial, parametrically trivial. And in particular, we expect that response function can be very strongly enhanced when we're driving phonons close to their equilibrium frequency. Okay, but now let me say a few words. Why do we even consider parametric driving of phonons? And the answer is that actually this is the model of how we go from external pump to photoinduced superconductivity requires some intermediate stages, and phonon nonlinearities play an important role here. So what the pump pulse does, it's a photon at zero momentum. You can only excite an infrared active phonon, the phonon that has finite matrix element to be excited by light, and also at Q equal to 0. But these infrared active phonons actually do not couple to electrons very strongly. They do not play such a major role in giving us PCS coupling. However, they have sufficiently strong coupling to Raman phonons, which do not couple to light directly, but they couple to electrons and they couple to the infrared phonons. And therefore, there will be a sequence of coupling that the infrared active phonons at Q equal to 0 can induce, say, Raman phonon, and nonlinearities of the Raman phonons. They can, you can see that they actually transfer the drive from the coherent part of Q equals 0 phonon to all the finite Q. Right? So therefore, as soon as we are looking at phonon nonlinearities, even though light is driving us at Q equal to 0, it can actually excite pairs of phonons at finite Q. And in fact, we get a Hamiltonian which looks exactly like parametric. Right. Okay, so I'll skip the more technical part of the derivation of the analysis, how one can analyze this electron-phonon system driven out of equilibrium. Let me just summarize some of the key points. So what this is really due to the hard work of Mertash provided. So what we're looking at here is spectral function of electron. This is something that angular of photoemission would measure. And this is a function of time. We start at times before the system was driven, and then we end sort of like here the pulse comes in and changes the spectral function. So what I want to point out is that this dispersion has a kink. If you haven't taken solid state classes, you probably haven't seen this, but this is kind of a smoking gun signature of electron-phonon interaction. It's known that because of interaction with phonons, electrons change the dispersion and energy of the order of the phonon frequency, the Debye frequency. And just by looking at the change of slope, one can tell the strength of electron-phonon interaction. Also, by looking at the width of this peak, we can tell about the decay rate of electrons. And here you can see that at the Fermi energies with frequency equal to 0, we have a very narrow line, right? Which means that actually we have very sharp Gaussian quarters. Then, as time progresses, the spectral function, okay, it may be harder to see on these plots, but the slope changes, the kink is getting larger. Well, this is sort of amplified here. This is basically, you know, the fact that we have a different slope close to the Fermi surface means that we have a different mass. And the stronger is the electron-phonon coupling, the larger is the mass. Right? So if we look at the effective mass as a function of time, which is the same as just basically what measuring the slope of this line, you can see that the effective mass actually increases. Right? So we are indeed getting enhancement of electron-phonon interaction, which is good, which is what we want for photoinduced superconductivity. But at the same time, we see that the spectral function is getting wrong. So actually, our electrons are becoming less coherent, and this is bad for superconductivity because pairing is a coherent process. So we have to analyze competition between the two contributions, kind of the good side of the drive, which is enhancement of electron-phonon interaction, and the bad side of the drive, which is making electrons less coherent. So again, the technical details are not so important. One can solve the so-called Ilyashberg equations from, just for those of you who studied BCS theory, I remind you that this is like solving the BCS self-consistency equation, right? So you introduce a gap and then you ask, okay, what is the interaction, the value of the interaction when I can have a non-trivial solution of this equation? It can be as a function of interaction strength or as a function of temperature. So Ilyashberg theory is sort of the same type of idea. You're looking at certain eigenvalues, and when they become negative, this means that you can now have a non-trivial solution which supports superconductivity. And so as we watch this Ilyashberg as eigenvalues, we find that they start being positive, meaning that before the pulse comes in, we're looking at energy above DC, there is no superconductivity, but then after the pulse arrives, these eigenvalues cross zero, they become negative, meaning that now the system can support superconducting state. But unfortunately, this is only a transient state, and the reason it's transient is because Gaussian particles become incoherent, and that's why we can only so far the electron state, this photoinduced superconductivity has been short-lived, although recently they actually achieved quite remarkable increase in the lifetime of superconductivity. superconducting state by Watershed magnitude. Okay, so go into actual numbers. So, but just to summarize, let me give you another perspective on how to think about enhancement of electron-phonon interaction. Let's again take our example of equilibrium systems, right? So we know that effective attraction between electrons is g squared divided by the phonon frequency. So if you want to enhance electron-phonon interaction, you want to find systems where the phonon frequency is small. And that's why you often find superconductivity at some kind of structure, close to the structural phase transition or charge density wave transition, basically close to the points where the phonon frequency has to go through zero. So in essence, what we're describing here is a dynamical, non-equilibrium version of the same thing. So we know that if we drive the harmonic oscillators parametrically, they become unstable, right? So and therefore they become unstable because they're about to become unstable. They become very susceptible to external perturbations, right? So this shows us the stability phase diagram as a function of drive amplitude and the driving frequency. But the idea is that while we know that if we drive sufficiently strongly, then we know those harmonic oscillators are about to explode, and therefore if we think about how they respond to the perturbation given by the first electron, this response of such photoexcited phonons will be much more dramatic, and that's where amplification of electron-phonon interaction comes in. Or we can also think about it as softening of the phonon frequency, but now this softening arises not because we are close to the equilibrium phase transition, but because of this parametric drive. Yeah.
So if we include, let's say, a nonlinear potential of these phonon modes, as we parametrically populate these phonon modes, the frequency would depend on their occupation, so they would become DQ, like a nonlinear steady state. When that happens, would that stop the enhancement? Once you have populated enough photons to like make your phonon mode enough?
It does happen, but you see, in essence, what we want, because we don't actually due to nonlinearity, what one finds is that indeed phonons change their frequency, but it works usually in the direction of making phonons somewhat softer, even in the time averaged sense, which is good for superconductivity. So you are right that this actually makes parametric resonance less effective, but on the other hand, it makes them also softer, which increases. But in what we saw, if you think none of these seem to play particularly important. I mean, so all of this things are happening. And okay, quantitatively, I'm not sure I would be able to tell you, okay, this accounts for like 30% or 40%. You should just really look for a change of the kind of spectral function, including the change of the resonant frequency, or changes in the of the lifetime of the phonons. So it's just have to keep track of all of these things together. But yes, it is part of the story. Another question. Okay, actually, interestingly, that this idea is not, we sort of rediscovered the idea that has been known from before for people who say work in optomechanics. So it's a trick that they came up with that when they wanted to amplify interaction between photons and phonons. And what they realized is that actually in order to make interaction larger, they just have to turn either photons or phonons in a squeeze state. And that's effectively what we're doing by parametrically driving phonons with making a squeeze state of phonons, which makes the interaction with electrons larger. Okay, but how do we connect it to let's say this kind of amplified light, the type of reflection coefficient can be greater than 1. So let me first throw at you some results, and later on I'll explain, sort of as we go with these lectures, what's the technology for doing these calculations. So what one can do is, let's ask about dynamics of non-equilibrium superconductors. So imagine that I start with electron-phonon system, and then I suddenly change my electron-phonon interaction strength, right, just by hand. Of course, it's not something you can do experimentally. So we saw that, okay, like parametric driving gives us something along these lines, but it's not the same as just literally changing by hand. But for now, let me just change this electron-phonon coupling by hand. So we started with a Mexican cat having a minimum here, and then let's say, for example, let's say just having a kind of a shallow minimum, and then we suddenly make it deeper. And then what we will do, we will watch the dynamics of the order parameter as a function of time, right? So in this specific calculations, what's shown is that we start with some so this axis basically tells us the initial value of electron-phonon interaction, but we always change it to 4, right? So basically, like 4 here means that we did not change the electron-phonon coupling at all, and so this is the color coding of the gap, so you can see that the gap just doesn't change, right? So here, again, it's a slightly simpler problem where we already start with the superconducting state, and then we see how it responds to changes of the electron-phonon interaction. But as soon as we start with a value of interaction which is either small or large, which is different from our final value, and do this quench, then we see that actually the gap has some kind of oscillation in time, right? You can clearly see some kind of time-dependent pattern. And when we analyze this time-dependent pattern by just taking a Fourier transform, what you see here, okay, let's just look at this blow-up. So this is basically the same plot, but instead of time, we show frequency. We see that it has very prominent Fourier component. And in fact, for very small quenches, the frequency matches this quasi-particle continuum to delta. That's exactly what the Higgs excitation should be. For larger values, we see frequency which is somewhat renormalized, but it's clearly a very close cousin, right, of this excitation to delta. So this tells us that if we suddenly change electron-phonon interaction, then we will not have some kind of gradual evolution of the superconducting order parameter, but we'll have oscillations. And then we can even solve this somewhat more realistically. Instead of suddenly changing electron-phonon interaction, we do parametric driving just the same way as we discussed happening in experiments. Again, you see oscillation. If you do Fourier transform, again, we see this very strong contribution to delta. So by suddenly driving the phonons, which enhance electron-phonon interaction, therefore we do excite the dynamics of the superconducting order parameter. The amplitude of the order parameter starts to vibrate at the frequency of the delta. Okay, and now what I want to do is connect this picture. Just an idea that if we suddenly change the Mexican cat, we get the dynamics of the order parameter, which is oscillating, to this very unusual optical response when we can get a reflection coefficient of light greater than 1. Right? So where does this come from? So I want to show you that actually this optical gain, which we saw from experiments, is naturally connected to the Higgs oscillation. So actually the basic idea is very easy to explain. So Higgs excitation, right, is a finite energy excitation. In fact, if we think about, say, superfluid systems, right, remember we said that it's an excitation with a finite energy, and if we look at dispersion, omega versus k, it has finite energy at k equal to 0. But we also have Goldstone modes, which go to 0 at small momentum. Therefore, when we excite the Higgs excitation, it can actually decay into a pair of Goldstone modes in such a way that energy and momentum are conserved. And that's, for example, what determined with remember in this experiment with cold atoms, we saw that the Higgs excitation was not a very sharp peak, it was broad. It was really just decay of the Higgs excitation to this Gaussian mode. And the same can happen in a superconductor. We excited the Higgs mode, but it can decay into Gaussian-like mode. But what is a Gaussian mode in a superconductor? It's winding of the phase, and winding of the phase carries current, and that couples to light. Therefore, basically, Higgs excitation can decay into a pair of photons. And it can decay in such a way that the sum of the frequencies of these two photons must add up to the frequency of the Higgs mode. And in principle, if we just sort of excite the Higgs mode and left the system as is, all kinds of pairs are generated. But now when we send in a probe beam, right, we're sending photons at very specific frequency, omega 1. Then actually there will be bosonic stimulation, and therefore the pairs of photons which will be predominantly generated are the ones which match one of this frequency omega 1, and therefore what we will find is that when we are sending n photons with frequency omega 1, we will generate an additional omega 1, omega 2 pair. Therefore what will be reflected is now one extra photon at this incoming frequency, and also the kind of apartment photon, which is called the idler photon in the language of quantum optics, right? Something that's complementary to the Higgs frequency. Okay, so can we turn this kind of hand-waving idea into actual calculation? Well, and indeed this calculation is relatively straightforward, so let me just give you an idea. Later on I'll explain more details in a simple example. So basically, what we want to do, we want to solve the problem of light reflection. Right? That's what you learned in your introductory optics classes, the so-called Fresnel problem. But usually you solve it for, if you know, say, the dielectric constant, right, or the material refraction coefficient. But basically, what it amounts to is just solving Maxwell equation, which involves the current, and we have to know relation between the current or polarization and the electric field. And as we said, in superconductors at small frequency, this relation is very easy. So we say that the current is some superfluid density times the velocity of Cooper pairs, and these Cooper pairs are accelerated by the electric field. Right? The time derivative of the electrons is proportional to the electric field. And usually when you solve light reflection from a superconductor, like you just take the superfluid density as a constant, right? But in our case, as we said, we're looking at a state in which it's not an equilibrium superconductor, but rather a superconductor with an excited Higgs mode. Therefore, its superfluid density is oscillating in time. Right? Therefore, now what we need to do is solve these Maxwell equations, right? When the superfluid density is oscillating in time. And okay, I'll show you how this works in a simple example later on. Now let me just point out that yes, actually, when we go through this procedure, indeed, we can get sort of we take some numbers which are kind of reasonably reminiscent of experiments for the conductivity of materials. We do find agreement with experimental results of the Campbell. Okay, so how much time do I have?
You still have about 13 minutes? 13, not
13.
Not 13.
Okay.
You have 2 hours, Eugene.
So let me point out that we saw this in superconductors and Higgs. This effect is hopefully much more generic. So for example, if you there is a class of materials which are called incommensurate charge density waves. So in the case of basically, so this is modulation of the density, and at small frequency it's a true insulator because this density wave is spin by disorder. But there is usually a very good separation between the spinning frequency and the quasi-particle continuum. So over about like a couple of decades, this incommensurate charge density waves behave just like superconductors. So they obey the same London equation. And therefore, many of the things that we discussed for superconductors like this Higgs amplification should be applicable to these materials as well. And in fact, people have also seen Higgs-like excitation in in charge density waves. So in this case, these are just time resolved arcs, so they can measure the quasi-quad Fourier as a function of time, and you see this long-lived oscillation which correspond to the Higgs mode of the charge density waves. Okay, but now, I didn't show you all the details of how to actually get like amplification in the case of a Higgs mode, and I did this so that I sort of have an excuse to introduce another system which actually shows very similar physics, but kind of simpler setting, yet it actually has even more dramatic consequences. And so again, we will sort of analyze like a Fresnel problem. Basically, it's a problem of light reflection from a medium, but it's a medium which is not stationary medium. It's a medium whose parameters are modulated in time. Remember, that was the first one of my introductory slides by saying, oh, we can really now think about controlling properties of materials using some kind of time modulation. And so that's the kind of problem that we want to consider, but in the simplest possible setting, and that's an insulator. But indeed, actually, this again can be connected to experiments also done in Cavalier's group, but this experiment was done in a very boring insulator, silicon carbide. And one can explore it, but on the other hand, it actually is known to have very strong coupling of phonons to light. And what was seen in this experiment, again, in pump and probe experiment, so they started by resonantly exciting phonons. So they just sent a very strong pump field, and then they did it against the probe experiment. After some time, they sent it light and looked at the reflection coefficient. And what they saw is that again, after they excited the phonon, they could get reflection coefficient greater than 1. Again, the material became an amplifier. Right? So somehow we changed the electromagnetic properties of material by pumping it initially. Okay, so how do we understand this? So now, first of all, how do we describe the system? So the simplest way to understand these materials is to think of a phonon. So we have this kind of infrared active phonon, and let me start by basically plotting its dispersion as flat. Okay, you can have some dispersion, but it's much smaller dispersion than dispersion of light. Right? And now we have to hybridize these photons, right, which have linear dispersion with the phonons, so we get upper polaritons, right, and lower polaritons. So when I said that the first pulse strongly excited phonons, in reality they strongly excited the upper polaritons. Right? So if we just had linear theory, then the way to describe this hybridization would be as follows. We would again have to solve Maxwell equations. You see, it's again Maxwell equation, but now instead of current, they just use the time derivative of polarization. Now we have to sort of add equation which tells us how polarization depends on the electric field. And this is can be obtained just by looking at the coupling between the phonon displacement and the electric field, and we said, oh, in this case, a phonon is infrared active, therefore it can couple linearly to the electric field. And then it's also a harmonic oscillator, right? It has some finite spring constant. So therefore, if we want to compute polarization, we just take the derivative of the energy with respect to electric field, right? And we find that, okay, so there is the usual susceptibility of vacuum to electric field, and then there is also a component which is proportional to the phonon displacement. So and on the other hand, if we want to write equation on the phonon itself, right? So you see, it's basically an equation of we write that the time evolution, right, is given by the force, and the force is just derivative of the potential with respect to the phonon coordinate. So the right-hand side of that just gives us shows that it's a phonon, right? Gives us a phonon frequency. But now there is also a contribution from electric field, which is driving the phonon. And at the same time, right, that we have this relation between polarization and electric field, we can put it into the Maxwell equation. Actually, we can condense two Maxwell equations into just one equation on the electric field. So now we have to solve together these two equations, and that's how we get this upper polariton and lower polariton. in this case, we know that we should look for interesting nonlinear effects. And in fact, you know that nonlinear effects can come from the fact that, say, the susceptibility of the material, right? It's something we can think about as really the electric constant at infinity, right? May depend on the phonon displacement, right? And somehow phonon can change polarizability of the matter, right? And by symmetry, it should only come in as q squared, because just by the inversion symmetry, we cannot have odd powers in the energy. And on the other hand, the matrix element of coupling phonon displacement to electric field, we took it to be a constant, right? And we consider simple linear coupling, but it may also have higher power of the phonon displacement, right? So these are two very naturally nonlinear terms that appear. And therefore, if we write the same equations as before, right? We just write equation on the harmonic oscillator on the phonons and Maxwell equations, we see that we, in addition to the old terms, kind of linear terms, we now get nonlinear terms. Right? And effectively, when we calculate the Bayer dispersion, what we do, we just linearize these equations of motion, like Maxwell equations and dynamics of a phonon, in around the vacuum state, around the state in which there is no phonon displacement, there is no electric field. But now what we have to do, we have to linearize, like after the pumping, we have to, when we look at the probe beam, and it's important to keep in mind, so the first pump is very strong. It really very strongly excited the phonon, but then the probe pulse is very weak. So we can do linearization with respect to the probe pulse, but we have to be non-perturbative with respect to the pump. And therefore, we have to take a solution which corresponds to the strongly excited state in which we have a large number of phonons at zero momentum and a right linearized equation around that state. So therefore, right, we take these nonlinear equations and we say, oh, our phonon displacement, right, they have this component which comes from pumping, right, and that's just our phonon frequency at zero momentum. An electric field has a very strong component which is due to pumping. And then we also have small component which is due to the probe beam. And notice that I already take into account that kind of frequency mixing. Remember, we talked for a superconductor, this mixing between a signal and an ion. And you can already see this here. Right? You see, when we write the electric field, but q squared, if I think about, let's say, q squared coming from this pump, this is oscillating at frequency which is twice the phonon frequency, which means that in this equation I have this time dependent, I have this something which is analogous to parametric, right? I have frequency mixing, exactly the same mixing between signal and ion as we discussed before. Therefore, when we want to solve a linearized problem, just at this point we're just calculating eigenmodes, like how we were calculating Polaritons, but when calculating Polaritons not in a static medium, but rather by calculating Polaritons in the Floquet medium. And this and the Floquet eigenstates have to have superposition of several frequencies, and in this case we just restrict to the two most important ones, which is signal and ion. And in order to find the amplitudes of signal and ion, we actually have to solve now a 2x2 matrix. Okay, anyway, so one can do this, but now we also understand how to solve the light reflection. So when light comes in, right, so in vacuum, of course, we don't have any modulation of the dielectric constant, right, so we just have light, incoming light at the signal frequency, but then it falls on the medium. The medium is modulated, right, with the phonon Polaron frequency. And so if we think about the eigenmodes in the medium, they're now superposition of the signal and idler frequencies, right? Which means that this incoming light will excite not only the signal, not only light at the signal frequency, but also the idler frequency, and therefore what will be reflected is again signal and idler frequency. And that's exactly what we have to do. Then we have to do the usual kind of matching conditions, right? So we have light coming in, we have reflected and transmitted light, but now for transmitted light, our eigenmodes, we have two sort of Floquet eigenmodes. Because remember, you can think about it this way, without Floquet drive, we had two separate modes, omega signal and omega either. Now we mix them up, but the number of modes stayed the same. We still have two. Therefore, if we come in at the signal frequency, we will still excite two Floquet eigenmodes, but every one of these, like you do with the usual Fresnel problem, like continuity of the parallel component of electric field, continuity of magnetic field, and so on. And when we do this, well, first of all, okay, so this shows us this reflection coefficient as a function of frequency. So the green line is when there is no drive. And so what you can see, again, something which is basically what we saw in the experiment, there was a reflection coefficient close to 1. So this is actually, this is in the regime between the upper and lower Polariton band, so-called Electron band. But as we start introducing pumping, right, if we pump the system before, we find that reflection coefficient just suddenly explodes. So we can get reflection coefficient in the simplified model, which is extremely large. But what is even more remarkable is that actually it's something that one doesn't find in the usual reflection Fresnel problem. We get discontinuity in the reflection coefficient. Right? That's something very surprising, right? So everything should be a smooth function of frequency. So why do we suddenly have discontinuities in the reflection coefficient? So actually, this turns out to be a very interesting feature that, just like in many-body physics, if you want to analyze collective modes in a system, what you do, you just look for poles, right? Basically, let me just remind you that, let's say, if we look at magnetic systems, we can usually we write a relation that magnetization, right, at finite q and omega is response function q and omega times h, external field of q and omega. And for generic q and omega, you say, oh, in order to get magnetization at this q and omega, I have to have external fields. So, but there are special wave vectors and frequencies where you can get finite magnetization with zero field, but they require chi of q and omega equal to infinity, or they require looking at poles of chi and q and omega. And they correspond to collective modes. Right, so that's the usual trick of doing many-body calculation. If you want to analyze collective modes, you just look at the response function and ask where does it have a pole. And that's something that you can do here. You can calculate reflection coefficient as a function of frequency, as a function of complex plane. But now you find that actually the poles move into the upper complex plane. And of course, what this means is that if we look at a collective mode, right, so if we're looking at something e to minus I omega, let's say collective mode times t, but now we say, oh, actually the collective mode has real part, omega prime plus I omega double prime, and omega double prime is positive. This means that this will go e to omega double prime times t to minus I omega prime t. So we get that something is growing exponentially in time. So we get effectively lazy. So indeed, what this analysis shows us is that in this seemingly simple system, silicon carbide, what the pump pulse has done, it created kind of a lasing instability. But in fact, this lasing instability has a very simple physical interpretation. It's a statement that, so we created a large number of phonon polaritons, right, at the bottom of the upper polariton band. And it turns out that you can find a very special value of momentum and frequency where you can take two of these phonon polaritons and scatter them. One stays in the upper band, the other goes to the lower band, in such a way that energy is conserved and momentum is conserved. And that's exactly the lasing process, which actually shows up as unstable collective modes. Okay, so now I sort of basically close to conclusions. I think you know, this type of physics is it shows that nonlinear optics can be a new interesting tool for probing many-body physics. That you know, we can see let's say Higgs excitation, other types of excitation. You can actually ask Marius about other interesting types of excitation one can probe use sort of with this flavor. But it's also interesting that this occurs in this kind of very important frequency range terahertz. You know, we sort of have good technology in microwave. We have sort of good technology starting with the infrared. The terahertz is extremely hard range of frequencies to work in, and maybe now we can hopefully use these techniques for getting devices such as frequency converters, amplifiers, maybe even use some kind of for applications in quantum computing, since you know this kind of Higgs amplifier is generating entangled pairs of phonons. Okay, so I think I'll just stop here.
Thanks, Eugene. So we probably have some questions.
So let's say we have a collection of modes that become unstable, that have this imaginary part. Does the imaginary part magnitude matter? Would we say that the largest imaginary frequency dominates everything else?
Right. Usually, the what comes out is that yes, the one that grows the fastest is dominant. Of course, it's a tricky question, because you can say, well, it's exponential growth of something that you had to begin with. Maybe the initial seed for the most unstable mode was so much smaller that sort of the subdominant one started with a larger value and grew faster. But usually the strongest mode wins. But of course, a more careful, precise analysis would really have to take into account kind of feedback, because this is just analysis of these modes where they don't talk to each other. Right? Just saying every one of them grows independently of the others, but when they become large enough, they start suppressing each other.
Let me ask one question actually about this last part. So you said it's lasing. There was also due to the return, so or there can be interactions also between those polaritons. As you show.
Oh, fundamentally, right? We start with the interacting theory.
Actually.
Also, but in this case, right? Okay, if you go to this picture, this is not really a BEC, right? You just pump at this frequency. Like
right.
This condensate you put by hand.
Right, but you said it's a laser.
But after that, right, you can say that when we start thinking about phonon polaritons, right, at these new frequencies, this is like a lasing instability.
Okay.
But in fact,
So, Eugene, do they
yes.
have a difference in lifetime, the upper and lower polaritons? Because otherwise, isn't this like a parametric down converter, or parametric amplifier more than a laser?
I mean, in this case, okay, I guess what we see is we didn't really study the fate, right? Once you generate them, what happens to those photons? We just studied, okay, mostly we see its signatures in the reflection coefficient. So you are right to say, okay, well, after we generate these pairs, maybe the one which has the largest phonon component decays much stronger, because most of our damping just comes from the phonon. That's why, presumably, on the other hand, they're kind of, well, okay, I guess this one is somewhat closer in frequency to the original phonon, and that's why it may be shorter lead.
I just didn't want them to Rabi oscillate back. So if one has a nice short lifetime, then you don't have a macroscopic occupation of that one. But maybe that's not the lines you're thinking.
So I think, this is sort of beyond analysis that we know, right? Because we're just looking at the initial instability, and that's something that may happen at later times, which would be interesting to think about.
Is it a lasing instability in the sense that if we have a couple of unstable modes, we can selectively pick one by the probe? As in the probe will populate one of these polaritons and will preferentially make it down convert into that mode versus others?
No, it's lasing on actually in the same sense as a gain medium. So imagine that you solve the problem of light reflection, but not from the usual medium that has losses, but rather a medium that amplifies light without changing its frequency, like a gain medium. Right? So that's what we call lasing, it's just a gain medium. So if you calculate, again, do the same exercise of just, you calculate reflection coefficient, and then you look for the poles of the reflection coefficient, you find that they may be in the upper half plane, meaning that these are now unstable lasing modes. So what this, of course, this in principle slightly different question, because in light reflection you're still assuming that there is a probe pulse that comes in and gets reflected, whereas lasing says, oh, I don't need a probe pulse, I mean the system will light up by itself. Right, so, and the same is here, strictly speaking, we don't need a probe pulse that if we pump here, we expect that due to this process, we should start getting light at that frequency, those two frequencies, later on by itself. Whatever the initial quantum fluctuation will be enough to initiate the runaway.
Let me resume my role as the chair class one more. So you showed the variations or the oscillations in delta, the Higgs mode at this frequency, and it was actually quite substantial. It was like 10% or so variation in the gap. So what I wanted to ask is,
it's superfluid density.
This was superfluid. This was not the gap.
Right. Yes, because what we need.
But the gap would also.
That's an interesting question. So if you remember VCS theory actually at zero temperature, the superfluid density does not even depend on the gap.
Right.
However, close to TC, they both scale as square root of TC minus T. So what we need for our analysis is really modulation of the superfluid density.
And wouldn't you also have, or wouldn't you expect also to have oscillations in the gap?
That's right, but the gap only affects quasi-particles. And response of quasi-particles is important at high frequencies above 2 delta.
Right.
Because what we describe, Lambda equation only describes the motion of the condensate without the quasi-particles, right? And that motion of the condensate is controlled entirely by superfluid density. So I think what you're asking is, okay, what happens at high frequency? Because now your quasi-particles are also kind of like modulated.
So let me say why I'm asking that. Let's assume you would place magnetic impurities on top of your superconductor to verify your theory. You would have Shiga-bound states in your system. And if they would seem or suddenly varying the gap, you should see in STM a shifting resonance in STM to Shiga-bound states to verify your theory. But that would require a change in the gap over time.
So I think you're very ambitious. So one of the challenges of this experiment, the superconducting state lives for picoseconds.
Mm-hmm.
Now they have actually new results.
But they showed something with an STM effect somewhere.
That will be the final part. So that will become a different story. Right? Now they say they can extend it to nanoseconds, but it's still so much sort of shorter than anything that you need for conventional transport, STM, and so on. So that has been one of the challenges that the toolbox that you can use is very strongly constrained. You have to do very fast probes.
So there would be no way to measure directly the Higgs oscillations. Because right now it's an indirect effect. You see the enhancement in
it's coupling to
because they decay
both the modes, right?
mode, they couple to current, and then the current makes reflectivity.
Right. At this point, No, it is an interesting question. So I think what you're arguing is, or what if you measure something which is affected by the quasi-particle gap? Like, so okay, maybe I take it back. Let's say if they do time-resolved ARPAs, right? Because time-resolved ARPAs really measures like the energy of quasi-particles. Just like in the case of charge density wave, we saw this gap going up and down. So that would show oscillations of the gap, and therefore the Higgs moment directly. From what they tell us, they tried very hard, but just so far it didn't work out. So we couldn't do ARPAs on this material.
Right, do we have any more questions? Everybody's ready for dinner? All right, let's thank you, gentlemen.